Okay, people. Today, a little bit about atomic forces. So, in physics, we have electrostatic forces, we have gravitational forces, we have the strong force, we also have the weak force. The strong and weak forces to do with atomic physics. The electrostatic forces to do with charges attracting and repelling, and gravity is to do with gravity, masses attracting and repelling, or attracting. The strong force, though, is to do with the attractive or repulsive properties of protons and protons, neutrons and neutrons, or protons and neutrons. So sometimes it's referred to as the nucleon force because it's between nucleons. So a nucleon is something that lives in the nucleus, just like an Australian is someone who lives in Australia. Nucleon is something that lives in the nucleus. So this strong force is something that makes things attracted to each other, so proton, proton, neutron, neutron, proton and neutron, attracted to each other regardless of their charge, regardless of their mass, just based on this interaction or exchange of particles between protons and protons, neutrons and neutrons, and protons and neutrons inside the nucleus. So when they are somewhere around about 0.7 femtometers, so you've seen millimeters, you've seen micrometers, you've seen nanometers, we've also got femtometers. So nanos minus 9, femtos minus 15. So we're about 0.7 femtometers away. Really super repulsive. So this force, you can't squish neutrons any closer together, you can't squish protons any closer together. Somewhere around about 1 femtometer, so 1 by 10 to the minus 15. This is actually an attractive force, so anything above the graph attractive, about 2 to 2.5, give or take, it becomes repulsive again because we have other forces interacting here as well. So this nucleon force binds things together, binds the nucleus, I guess, together. Otherwise, if there wasn't something that's holding protons to each other, you just have the electrostatic repulsive force, and then you wouldn't have anything able to exist, really, other than protons whizzing around kind of aimlessly. The size of stable nuclei is actually directly related to this. So nuclei have to be, nucleons have to be this far apart. They're repelled until they're about that far apart, and then they're attracted and held together somewhere in this range. So depending on how big, so carbon, we'll go back to last video, carbon-12 is stable. It's got 6 protons, 6 neutrons in it, but if we add just one more neutron, we get this. And what we've done is we've changed the size of the nucleus. So now this doesn't have enough nucleons, so the internucleon forces within its nucleus to hold it together. So this last little neutron here makes this one unstable. This one here, unstable. And something that's unstable, we sometimes refer to as it being radioactive, or it's a radionuclide or something similar. So carbon-13 we actually use for carbon dating, radioactive emissions, that sort of thing. Use it, we don't suffer from it so much because it's unstable. Its nucleons are now spaced a little bit too far apart, so one proton over one side and a proton over the other side are actually repelling each other based on the electrostatic repulsive force. So we have the nucleon force, which binds things together. We have, I'll go a different colour, we haven't had green for a while, we have the electrostatic force, remember from the electric stuff we did way back in term 2, and this repels like charges, remember? So protons on one side of the nucleus, so I'm not going to draw all of the protons, but let's say here's our nucleus like this. These protons will vibrate. They're not fixed in there. They will vibrate backwards and forwards until we get one of these protons, shifts a little bit too far away from one of the other ones, and now this is outside of this attractive range. And the reason it turns repulsive isn't because they're too close together like they were here. It's actually because now the other force that's involved is bigger. The electrostatic force is now here, the electrostatic force is greater than the nucleon force. So we've actually got a tug of war where the electrostatic force is now winning, which means that this thing here is unstable, which means that one of these will disappear, and or both of them, or something will happen. This is unstable, it will decay, undergo radioactive decay. So we have these unstable nuclei. and they are scattered all over the periodic table. Have a look at the front of your diary, have a look at an app on your computer, whatever you want, and you'll actually be able to find the unstable nuclei. So generally what we have is N, number of neutrons, Z, number of protons. If we draw a straight line, that's the N versus Z graph, or the slope is 1. So 25 protons, 25 neutrons, yada yada. But the start of that, down the bottom here, where we have things like carbon 12 and lithium 6 and all those other ones down the bottom, up to about, say, 22, 23, give or take, I can't remember the exact number, it might be 23 or 4 even, 1 for 1 proton, 1 neutron, stable, nice and stable. But once we get too big, so this kind of scenario, we don't actually get anything that's, you know, stable on this line. So we get to the point where adding an extra proton will instantly make things unstable. Adding an extra neutron though, because neutrons, remember, are neutral, they don't repel because there is no charge, they'll only undergo this nucleon force. So our graph over here can sort of shift a little bit to the right. I don't actually know what it would look like, but let's kind of draw it. It might be something, I have no idea. But we don't have this repulsive part of the graph that made this one drop down. So it's, you know, it's able to be a little bit bigger. So what we end up finding is that the stable stuff is kind of on this curve. That's not really a curve though, is it? Where we have, let's try and keep on making it worse, aren't I? Now I'm just coloring in. All right, so it's on a curve where we've got more neutrons to protons. So our N versus Z ratio is bigger. So we use extra neutrons to kind of glue this thing together, using the nucleon force that the neutrons have to glue this thing together. We get to the point where at lead, that's the heaviest thing that's got a stable version of itself. Anything after lead, there's no such thing as a stable uranium or stable thorium. They are all radioactive, they are all unstable because they're just too bloody big and they undergo decay because of it.